Hello, in this video we're gonna prove the second lemma of the theorem that states that a language is regular if and only if it's described by a regular expression. The second lemma states that if a language is regular, then there is a regular expression that describes it. For this, we will try to convert from a deterministic finite automaton to a regular expression. Why? Because if the language is regular, we know that there should be a deterministic finite automaton that describes it. We will be using this example to show the steps how to convert a DFA to a regular expression. So the input will be a DFA and the output will be a regular expression. Two important steps are there. The first one is to build a generalized non-deterministic finite automaton from the DFA. Then to take this NFA and start ripping out the internal states one by one and do the necessary changes. We mean by changes here the modification that we need to do on the transitions so that the machine still accepts the strings that are already accepted. So let's start by the first step, which is building the generalized non-deterministic finite automaton. In fact, generalized non-deterministic finite automaton is a non-deterministic finite automaton with some restrictions. We will have only one accept state. We will have no arcs going to the start state, and no arcs will go out from the accept state, and all the internal states will be fully connected. That means that each pair of two states will be connected to each other via transitions. And all the transitions will be labeled with regular expressions instead of symbols of the alphabet. Let's go back to our example and show how to obtain the generalized non-deterministic finite automaton. First of all, we will add a start state and relate it to the old start state by an epsilon transition. Let's name this state start. Then we will add an accepting state. Let's name it here end and relate it to the old by epsilon. Note here that Q2 is no longer final. The final state here, or the accept state, will be end. Then we will add all the missing arcs so that the graph will be fully connected, with the exception that the start state will not have any edge coming to it, and the end state or the accept state will not have any edge going out of it. Okay, so for start, we will complete the missing edges that go out of it. Okay, so we don't have an edge from start to Q2, we will add it. And we will put the regular expression empty set on it. Okay, and we will add an edge from start to end with empty set as the regular expression on it. For Q1, there's already an edge going to Q1, an edge going to Q2. We'll add another edge that is going to end, and we will put the empty set as a regular expression on this edge. Now for Q2, there's already an edge going to Q2 and an edge going to end. So we will add the missing arc, which is an edge going to Q1, and we will label this arc by the regular expression empty set. The last step here is to replace multiple arcs by one arc with a union on it. Okay, if we have multiple arcs here, A comma B comma C means that we are going from this state to another by A or B or C. So we will replace this by one arc, and we will mention on it the union between A, B, and C. We will apply this rule to this arc, going out of Q2 and arriving to Q2. We have two arcs, A, one with A and one with B. We'll change it by only one arc with the regular expression A or B. And here we are, we obtained the GNFA for our example of DFA. Now the step 2 consists of removing all the states of the initial DFA. This means that we will remove Q1 and Q2 from this machine. We'll do that by choosing one state, remove it, then make the needed change. We will change the remaining transitions on the machine, and we will repeat the process of removing until we remove all the states of the initial DFA. To explain the idea of ripping out any internal state, let's take this example. We have here three states, S, T, and R. If we are removing R, we will use this transition between S and T to write the regular expression that we would have checked if we went from S to T via R. Okay, so we will write here on the arc between S and T R1, since the direct way here is by making R1, or this means the union, we will go via R1, or another way. This way, there's a regular expression on it. Consider, for example, from S to R we have R2, from R to R we have R3, and from R to T we have R4. We will take the concatenation of this and many occurrences of this concatenated with this one. Okay, so it will be R2 followed by R3 star followed by R4, and we will write this regular expression on the edge that will remain between S and T. And here maybe in R1 or R2, R3 star, R4, maybe we will have to simplify it. And let's recall that we will use these rules for simplifying it. Epsilon concatenated to any regular expression is equivalent to this regular expression R concatenated to epsilon, and this is equivalent to R. Another rule says that R concatenated to empty set is the same as empty set concatenated to R, and it's the same as empty set. Anything concatenated to the empty set will result in the empty set. And finally, the union between empty set and R will be R. Let's go back to our example, and we will start here by removing Q1. Okay, we will remove Q1 and all the edges coming to Q1 or going out of it. Okay, we could have also started by Q2. We would choose one state, we remove it, then we will go to the next state and do the same thing until removing all the states of the initial DFA, here Q1 and Q2. So here, let's take Q1 and remove it. We will change the transition going from start to Q2 by adding the other option if we went from start to Q1, then from Q1 to Q2. Okay, we will write down here on the transition the other possible option if we went through Q1. Also, we will change this one by saying what will be the regular expression if we go to Q2 via Q1, and so on. Here the edge between start and Q2 will change. We will write the initial option that was already there between start and Q2. Here it's empty set, and we will add the other option. We write down here or, and write the option if we are going from start to Q2 through the state Q1. And we will write here what will be the regular expression if we will take this way. So we'll find here epsilon, then a possibility of going through the same state Q1 many times with the symbol A, so it will be A star, and then we'll have B in order to reach Q2. So we'll write here epsilon A star B. And all of this regular expression may be simplified to A star B, since epsilon concatenated to anything will be this anything, it will be A star B, and union of any regular expression with empty set will result in the regular expression. So we'll write here A star B. Then we will modify the edge going from start to end. We will write the initial regular expression here, it's empty set, or we'll write here the option if we are going through Q1. Okay, through Q1 we will find epsilon, again A star, okay, and empty set. We will write here empty set or epsilon A star empty set, and we know that anything concatenated to empty set will be empty set. Union empty set, the result will be the empty set. Now let's take the self loop on Q2. We will write here A or B, since the original arc from Q2 to Q2 is A or B, and we'll write down here or, and write what will be the regular expression if we will go to Q2 through the state Q1. We will write empty set, then A star, then B. We'll write here empty set A star B, and this will be removed because empty set concatenated to anything will be empty set, and the union of empty set with A or B will result in A or B. For the last transition between Q2 and end, we will write epsilon as the first option there, or the second option if we are going to end through Q1, we will take this transition. We'll write here empty set, A star, empty set. Okay, and empty set concatenated to anything will be empty set. And if we take the union with epsilon, we'll find the result epsilon. Now we'll consider this new machine and remove Q2 with the same method seen for Q1. Okay, we will remove state Q2 and all the arcs going to it or going out of it. We'll write the new machine, and we'll take this transition and write on it the new regular expression. We'll write here empty set, the original transition, or we will write here the regular expression if we are going through the state Q2. Okay, we'll write the regular expression here, A star B, then A or B star, because A or B here may be repeated 0 or more times. We will write A or B parenthesis star, and then we will write epsilon, and the result here will be will remove this epsilon because epsilon concatenated to anything is this anything, and we will remove this empty set because the union of regular expression with the empty set will be the regular expression, and we will write down here a star b between parentheses a or b star. Okay, now we clean out the diagram. We will find on this remaining transition the regular expression that we were looking for. That's it for the conversion from a deterministic finite automaton to a regular expression. You'll find in the next video another detailed example for this conversion. Thanks a lot.